It's a pleasure to introduce Dr. Indraksi Raychaudhuri from the University of Maryland. Welcome for this colloquium. And Dr. Raychaudhuri, she is a lattice gauge theorist and currently working on algorithms for quantum simulators at University of Maryland in a collaboration with Zora Davudi, I think Martin Savage also. She obtained her PhD from SN Bose Institute. Then she was a postdoc at IMSC, and right now she is a postdoc at the University of Maryland. The Indraksi, she worked in Hamiltonian formalism, including pre-potential formalism of lattice gauge theory. Currently, using those expertises, she is working on algorithms for quantum simulators. And today she will be speaking on towards quantum simulating non-abelian lattice gauge theories. So Indraksi, please.
Thank you, Nilmanita, for introducing and inviting me, giving me the opportunity. It's been a while. I have not spoken to TIFR, though I think I have given 2 or 3 talks previously to this audience. No, maybe not the exact audience, but this group at least. Okay, so today I'll be talking about our goal towards quantum simulating non-abelian gauge theories. Oh, eyes. Okay, so we all know that quantum chromodynamics is itself a fascinating subject in theoretical physics that describes the theory of strong interactions. And there lies some mystery in the theory of QCD yet, and most importantly, the theory of quark confinement is not yet known analytically. However, the lattice approach to quantum chromodynamics, or lattice QCD, provides a very good non-perturbative calculational technique that uses the classical computation that have used actually classical computation resources at its fullest over the last 3-4 decades and found many exciting results. However, even after using the largest available supercomputers, there lies certain problems in lattice QCD that cannot be there lies some kind of roadblocks. Those are mostly due to sign problem, due to the existence of the infamous sign problem. And also, since the lattice QCD is formalized in the Euclidean formalism mostly, so this study is not very suitable to study the real-time dynamics of the theory. Hence, in this situation, the community seems that quantum simulating or quantum computing for lattice QCD may offer some hope towards this problem, to offer some light, shed some light in this direction. And most importantly, presently we are facing a change of paradigm in the computation world. From the classical computation era, we are being prepared to enter into the quantum computation era. So as a theoretical physicist, what's our role in this time? First of all, our role is to identify the physics problem that would actually benefit from quantum computation. And lattice QCD has been identified as one of the major problem. And after that, our task is to formulate our problem in the language that quantum computer would understand. And specifically for these beginning days of noisy or the beginning days of quantum computation, it is very instructive to propose and construct analog quantum simulators that is specific to a particular problem of interest. And of course, there should be effort towards writing algorithms or for the upcoming universal quantum computers. For us, lattice gauge theorists, this set of job is particularly important and difficult because the lattice gauge theory computations in the classical computation era and the upcoming quantum computation era is completely different. That requires completely different theoretical framework. For example, the classical computation era, one was working with Euclidean formalism, whereas the Hamiltonian formalism is actually most natural for quantum computers. And also we plan to address different objectives. So I'd say that there is no such tension between the classical computing era and quantum computing era of lattice gauge theory, but they are kind of complementary to each other. And of course, the computational methods are entirely different. So as I mentioned, that the goal is to perform lattice QCD. But by QCD, we mean SU3 gauge theory in 3+1 dimensions. So at this beginning stage, of course, this is quite a difficult problem, a far-reaching problem. And it is too complicated to start with. So that's why people have been really interested to study simpler theories that have kind of qualitative features that is similar to QCD. One such strong candidate is U1 gauge theory, that is an abelian gauge theory that describes quantum electrodynamics. And it really provides a very useful test bed for the novel algorithms and to construct the quantum simulators. And this has been most popular. That has been particularly popular is the Schwinger model, that is even simpler, that is QED in 1+1 dimensions. So these lower dimensional theories have been explored at its fullest extent and also being explored now. It is not done. So here's a set of references. Like if you look at this first references, this is kind of a review from the European community. Those have been working with this this direction for past 10 years or so. And there are some more recent advancement, both in digital and analog computation to handle Schwinger model in this direction. Most importantly, there have been some real experimental demonstration as well. There has been actually 3 reports on this. This one is back in 2016, and these 2 are more recently, but they have studied Schwinger model for a very small size lattice, for example, just 2 sites, but this one, they have gone much beyond. They have studied quite a longer chain. But these are all results with Schwinger model, U1 gauge theory in 1 dimensions. There has been also attempts to analyze other gauge theories such as Z2 gauge theories, and there has been experimental demonstration in that direction as well.
So the previous studies were on quantum simulators or on real qubit systems?
So there has been both. For example, this review contains both reports, summary of both. Like these experiments, these are all analog experiments.
Oh, all of them are analog. So like quantum simulator, basically. Okay.
Yeah.
Okay.
Because the present days, and this one is, okay, this paper is a purely digital paper, and this one gives a universal and algorithm for real-time dynamics of lattice Schwinger model on universal quantum computers. So this one states that the resource that you require to simulate Schwinger model is, you don't have that right now.
Okay.
But it has all the details.
Okay, thank you.
Sorry, will you explain what is analog simulation versus digital quantum simulation?
I'll come to it when I describe that.
In short, you are pretending that you are doing a quantum computer.
Okay, so analog quantum simulator, okay, I may state it, although I'll describe it quite a bit detail. Like analog quantum simulator means that you have a theory that you cannot solve analytically or using classical computer. You have a Hamiltonian. You map that Hamiltonian to another Hamiltonian that you can control by a tabletop experiment. And you can tune the parameters. So it's a one-to-one mapping from one theory to another theory. Those are completely different. But then studying that theory that you can tune and control, you gain some insights and you obtain results of the complicated theory. That's the philosophy of analog simulation. So that is very problem specific. Like for one system, you have one particular analog simulator. And whereas the universal quantum computer or digital computation is more general.
Indrakshi, I have a question about this. Yes. So you're setting up a mapping. Essentially, you have got one Hamiltonian, and then you're kind of giving some dictionary between this Hamiltonian and the states on which it acts, and some other Hamiltonian and the states on which it acts. Right? That's the analog simulation that we're talking about. Now, we know something about something for a long time about such things, and that is universality.
Mhm.
Okay. Two Hamiltonians will give you the same large long distance physics if they have the same symmetries and so on. This has nothing to do. Are you using that, or this has nothing to at all to do?
No, this is not really true. In this, I mean, of course, the universality is there, but these two Hamiltonian that you are taking, they are not in the same universality class. For example, they don't have the same symmetry or that, something like that. For example, when we are trying to simulate a gauge theory, we are choosing some condensed matter system, say some Hubbard model type system that has nothing to do with gauge symmetry.
Okay, so isn't it also true? Isn't it also true that if you take a totally different symmetry, then you will never get the long distance properties of cube match?
I won't say that it means that the Hubbard model will ever show asymptotic freedom or something. That is not the case. Just we will see that partially the properties, for example, the dynamics, if you, the observables of this system is mapped to some observable in the other system that have some similar dynamics. That is how it is done. Not the property wise or some basic properties of the Hamiltonian are being considered to be equivalent. That is why these are.
To me, this seems like it violates universality, right? Because all you're interested in, so you are saying that you have observed violations of universality. You have a specific example of observation of a violation of universality?
I'm not very sure whether there is a demonstration of violation of universality, but as far as I know, this consideration of universality is not taken care into account.
But is it not there? How can two Hamiltonians give you the same result? Okay, maybe in different languages. Okay.
I will show you something. I will show you an example that I have done the work, at least in my work, that is completely
so let me wait for that, but I have a second question.
Yeah.
Okay. And that is this talk about Hamiltonian. Because in lattice gauge theory, I don't write down a Hamiltonian. If I want to write a Hamiltonian, then I have to do some, several choices, right? You know the choices involved. So how do you write that Hamiltonian? How do you convert the lattice gauge theory problem into a Hamiltonian problem? And then, of course, you'll tell us how you map it.
Yes, yes. So of course, that is what I mentioned in the last slide, that for lattice gauge theories, this is actually a difficult problem because the lattice QCD never thought about having Hamiltonian. But there exists a Hamiltonian formalism for lattice gauge theory. And so, but that has not been that developed as compared to the conventional lattice QCD.
You mean the thing that the electromagnetic? Sorry?
The Kogut-Susskind formalism of lattice gauge theory.
Yeah, right. So doesn't that involve also a gauge fixing?
You have to think about the Gauss-La constraint. There can be done gauge fixing, but gauge fixing always comes with the problems like reverb ambiguities and all. So gauge fixing is not that very, very convenient or appropriate always. Specifically, gauge fixing for Hamiltonian lattice gauge theories is very much difficult. That is why my work has become relevant, because I have a formalism where I mod out the gauge degrees of freedom and I formulate the theory entirely in terms of gauge invariant degrees of freedom. And that has been found.
So you'll tell us more about it. Okay.
Yeah, of course.
Yeah, thanks.
Yeah.
Indrakshi, I have one question. Can I ask?
Yes, please.
It's related to what Sorindu was asking. So when you talk about this mapping between the two Hamiltonians, is this mapping some kind of non-local mapping, which also breaks these symmetries? So there is the information of going from one Hamiltonian to the other, when you say that they may not have the same universality because they may not have the same symmetry. Is it hidden in this kind of non-local mapping that you are choosing?
there can be non-local mapping as well. There is no restriction that mapping has to be local. But as far as I know, all of the analog simulation proposals so far, it's not been, that's why the examples are very limited. You'll see only 3 very small, like 2-site problems. So this is a really small system. And a 2-site, like Hamiltonian lattice gauge theory, is mapped to a 2-site Hubbard model or something like that. So it is very small scale. When you go to a large scale quantum simulator, there will be issues that we're mentioning as well. But those have not been explored yet. This is just a beginning, very beginning of the field. So there is a lot of work that to be done.
Okay, I see. Because you see, it reminds me of those kind of transformation that in condensed matter people uses. Sometimes you have interacting systems and you make some non-local transformation that could make into non-interacting, and then you could solve the non-interacting problem. Are these mappings that you're talking is in the similar spirit?
Yes, they are in the similar spirit. For example, handling fermion, you will encounter non-locality if you do in higher dimension. So these problems are there as well. So this type of approaches are being considered as well.
Okay, thanks.
Yes, so where I was describing that, yes, so there has been much progress with Schwinger model. There has been some progress with Z2 gauge theory. These are the 2 experimental demonstration. For it's funny that this demonstration is kind of a single site theory, 2 staggered site theory. But when we want to go to the final goal towards QCD, we'll have to think about non-abelian gauge theories. The simplest example that one think of is SU2 gauge theory that actually captures most likely all the non-trivialities of QCD, and then it's important to study that. If you look at the progress for SU2 gauge theory, for the reasons and the complications that we discussed, there has been really very minimal progress in this direction. There has been some analog simulation proposals. These were quite old, I think starting from 2013 to 15, there has been few proposals, but none of them has been experimentally implemented. And I have heard from one of the authors of these papers that those were kind of science fiction. Those are not really experimentally realizable in practice. Very recently, there has been some implementation for SU2 gauge theories, and also only one for SU3 for a very small lattice, just a 2-placket system in the digital computer. And this is for 1-dimensional theory. This is a special case. But so why is that? Since there is so much.
I'm sorry, Indrakshi, I have a question.
Please.
You said 2-site problem, but 2-site, where's the gauge invariance?
Oh, here the gauge invariance lies in the site. So if it is yes, that is something that you can't say. Where is the gauge invariance for the 2-site problem? No, this is completely, to me, it's completely absurd. It's just a single site on your lattice. You can think about anything. So
I'm sorry, that's not an answer.
They could simulate the U operator, the link operator. They could simulate that. That's all, nothing else. Nothing that you can expect to.
So you mean the action is something like trace U?
Yeah, exactly.
Okay, thank you.
Nothing else. This is not a real.
Trace U is.
Okay. So as I mentioned that the framework that, as Shorendu was saying, that there should be some Hamiltonian framework for lattice gauge theory. Actually, that was there starting from 1975, but that has not been much popular in context of computation because the Monte Carlo computation relies on the other formalism or the original formalism, but it was there. If we quickly look into it, what the formulation says that this is something like that, the lattice is taken to be the spatial lattice is discrete and the time remains continuous due to a temporal gauging with the original theory. And then this is the Hamiltonian, where this has an electric part, a mass part, an interaction part. This is a matter gauge interaction part, and there's the placket term. So the canonical conjugate variables for this Hamiltonian are this electric fields and the link operator that sits on the link that satisfies this canonical commutation algebra. Now there exists, and this is the placket operator that one can define, there exists the Gauss law constraint. This is a local constraint at each of the lattice site. This is the Gauss law generator that annihilates any physical state. So the physical Hilbert space is defined by this condition. And of course, the original gauge theory Hilbert space is a much bigger Hilbert space. And okay, I'll come to it later. This is how the strong coupling vacuum of the theory is defined, and one can build the strong coupling basis by action of the link operator on the strong coupling vacuum. Now, this Hamiltonian is quite simple to analyze for E1 case because the link operator here just becomes a phase for E1 gauge theory, and you can do calculations. For Schwinger model, this Hamiltonian is particularly simple because this last term drops because it's a 1D theory, you don't have a placket. So Schwinger model is much simpler. For SU2 gauge theory, this becomes really complicated because now your electric fields become color electric fields, your link operator becomes a group valued matrix operator, and your matter field that you have locally at its side that also has many components. Like for SU2 in fundamental representation, it has 2 components. And most importantly, the Gauss law that I mentioned here, this Gauss law for non-abelian gauge theories is of this form, where this A is this SU2 index that can take values 1, 2, 3. Now you can readily see from this expression that all these components of Gauss law don't commute with each other. So it's not really straightforward to get a simultaneous solution of all the 3 Gauss's laws. And you need your physical Hilbert space need to satisfy this condition for all the A's. And for SU3, it becomes even more complicated because this A index then runs from 1 to 8 instead of 1 to 3. So we will, for the time being, let us concentrate on SU2 at first. The simplest case of SU3, the SU2 that you can think of is the one-dimensional case, just like the Schwinger model, where you drop the placket term from Hamiltonian. So you have one mass term in the Hamiltonian, fermionic mass term, you have the electric field term, and you have this matter gauge interaction term, psi-dagger U psi type terms, and you have this Gauss law. And this is your Hamiltonian. And this is the lattice that you have. This is one particular site. You have left electric field, right electric field, link operator on this link, same for the other link, and you have the matter content here. Now, in a very recent work, we have studied all the variations of the Kohut-Susskind formalism for SU2 with staggered fermion and in 1+1 dimensions. And we studied it from the perspective of Hamiltonian simulation, and to see that which formalism is better to proceed with, which one is practical to use with quantum computer, even if we look at with the scope of classical computation. So basically, we took certain variants, for example, from the same Hamiltonian. This is a one-dimensional case. So for this particular case, one can do a pure gauge fixing, fix the gauge completely, choose a pure gauge, and end up with a purely fermionic formalism. That has a long distance interaction, but this formalism has no boson, no Gauss law, nothing, just a purely fermionic theory. But that is very specific, this particular dimension. You cannot generalize it to higher dimensions. There are also recent works where from this Kohut-Susskind formalism using the Gauss law, these authors have removed the fermions completely and ended up with a purely bosonic theory. So there is this standard formalism. There is this, starting from this Hamiltonian, you can impose the Gauss law constraint and solve Gauss law. This is complicated, and what you get is a minimal basis, angular momentum basis. This is some formalism. And then there is another formalism that was most of my PhD works and previous works with my collaborators, where you do the prepotential framework, you reformulate the entire formalism in terms of prepotentials that I'm going to describe soon, and you end up with another new formalism called the loop string hadron formalism. This is the gauge invariant formalism. So we studied and we found that this formalism has some benefits over others. Okay, I must mention that there is also another candidate of this Hamiltonian formalism that has been most popular till date, that is called the quantum link model formalism, which was developed in these and many companion works. But the thing is that For SU2 gauge theory, if you take in 1+1 dimension, this quantum link model, whatever the Hamiltonian, their prescription is given, whatever the representation Hilbert space they deal with, you actually get a different spectrum. So it's, at least at this level, this is not the same theory. And I don't think no one knows for sure what will be the exact theory in this formalism that will describe the same physics as this. So this is another alternate way of proceeding towards the same problem. So this relies on the logic that Shorendu was talking about. They're arguing that these may be a Hamiltonian in the same universality class, but there is not really a concrete proof in this direction. Okay.
Sorry, I'm a little confused. May I ask, can you go back to the previous slide?
This slide?
Yeah.
Or the last slide?
So you are not, so all these 4 boxes, they are not rewriting these Kogut-Susskind Hamiltonian, is it?
They are rewriting this Hamiltonian, yes.
They are all rewriting. Then what
Yeah.
do you mean they're not being in the same universality class?
I'm saying this quantum link model is not in them.
Achha, so quantum link model does not start from the Kogut-Susskind.
No,
Okay.
This is a completely different.
Okay. And then just to take one example, when you say remove fermions, what does one do? If you say it in a few words.
They have a systematic prescription of using Gauss's law to remove by an extra bosons. They are adding one extra symmetry, extra Z2 symmetry to the theory that is taking care of the fermions. So fermion, that's a purely bosonic symmetry, but that has an extra U1 invariance. Now, when you take that U1 symmetry and put that cutoff corresponding to the UN symmetry to the infinity, then only you recover the original gauge invariant description of the Kogut-Susskind formalism. Because since this is a theory of bosons has to be dealt with a cutoff, because this is an infinite dimensional theory, and for practical computation, you cannot deal with infinite computation. You need a cutoff. Here, there exists one extra cutoff that comes with the extra U1 invariance that you have in your theory because of removal of these fermions.
One more naive question. The Kogut-Susskind formalism also starts from the A0 is equal to 0 gauge, right? So you were saying gauge invariant beyond that. I mean, within that gauge.
Yeah, I'm saying if you look at this slide, this is U1. This temporal gauge fixing gives you a special discrete site and continuous time. Now at each site you have a Gauss-Law constraint. This constraint.
Fine. Thanks.
So I'm talking about solving that constraint.
Yeah, thanks.
Okay, so yeah, I think I'm already half of my way. So I'll try to describe the toolbox that we are kind of relying towards this goal, that is the loop string hadron formalism. And I'll briefly describe some of its applications, both in the context of digital quantum computation and analog quantum computation. Okay, so there has been the prepotential formulation of gauge theories developed starting from Manu Mathur, and I did a lot of work during my PhD and my subsequent postdocs in collaboration with Ramesh Anishetty and also Manu Mathur, and also independently. So there we have a kind of a complete reformulation of the original Kogut-Susskind formalism in terms of Schwinger bosons, and that formulation exists for arbitrary gauge groups SU2, SU3, and SUN, and it's true for any dimensions. The main feature of this formalism is gauge invariance, and this is a completely loop formulation, that is in terms of loops, but not in terms of, the proliferation of loop degrees of freedom has been taken care into. So it's kind of an exact physical degrees of freedom. We describe dynamics of only the exact physical degrees of freedom. Now, recently, we have coupled this formalism with staggered fermions in collaboration with a grad student. He was David Kaplan's grad student at INT, and we have formulated what is we call as loop string hadron formalism. Now, the simplest case, again, that one can think of is take SU2 theory and 1+1 and 2+1 dimensions. So this is the paper that describes the loop string hadron formalism. So how does it do that? I described that earlier, that you have this is the lattice sites, and each lattice sites you have the electric fields, left electric field, right electric fields, and the link operator. Now, in terms of prepotential formalism, what one does is one can actually replace this electric field and link operator, this set of variables, by a set of harmonic oscillators. So this is a harmonic oscillator doublet. This is another harmonic oscillator doublet. And in terms of this, you can reconstruct the original electric fields of the theory as well as the link operator. Now, again, another important feature is this link operator in this formalism it's a product of two parts. There is a left part that is only in terms of left oscillators, and there is a right part that is only in terms of right oscillators. Now, this reconstructed E and U satisfy the same algebra as the original theory. So they keep all the symmetry properties intact. And so but the feature is that with this formalism, you are basically breaking the link into two parts. You have a left part and a right part. Then what connects these two is an abelian Gauss law that states that this total number of oscillators here is actually equal to the total number of oscillators at the right end. This is the statement of this that we name as abelian Gauss law. Now, this is not something very new in terms of prepotential formalism or loop string hadron formalism. It was there in the original Kogut-Susskind theory. This is just a reflection of the constraint that your left electric field and the right electric field, these two representations satisfy the same Casimirs. They have the same Casimirs. And if you just use this expression here, you will get this relation, so that the number of oscillators remain constant. So this is kind of a link between the individual lattice sites in this prepotential formalism. Now, what is the major benefit of this formalism? Now, let's look at this one particular site. This is the site in the one-dimensional lattice. There at this site, we have some fermions. At this end, we have some bosons, as I described, the variables as a variable of the theory. And at this end, we have another set of bosons. Now, with these set of local constituents, all of those transform under fundamental representation of SU2 sitting at this particular site. One can actually construct local SU2 invariant operators. So what are these local SU2 invariant operators? These are all the set of invariant operators. This set is, you can construct gauge singlet out of left and right bosons. You take this, construct an intertwiner operator that is a gauge singlet, and that we call as pure gauge loop operator. This is a gauge invariant operator. In that sense, it is a loop operator, but it is defined at one particular site. So there are this type of operator. There are this set of operators, which we call incoming string operators, which are gauge singlets constructed out of left bosons and fermions. So these are kind of these boson and fermion. This is the incoming string part. Similarly, you can construct outgoing string operator out of this fermion and this boson. And you can also construct hadrons, which are purely fermionic singlets sitting at the lattice site. However, this hadron operator, actually, you can rewrite in terms of the other two operators. This is not really very independent operators. And we have the a closed algebra between all these operators. So these are basically the complete set of local gauge invariant operators that can one think of at this lattice site. Okay, now with this formalism, what the benefit is, now if you just look at these operators once, here is some operator, here you'll see both are dagger operators. So acting on a vacuum, strong coupling vacuum state, it will create something. Unlike these one, these has annihilation operators, so we'll annihilate the strong coupling vacuum. So same for each set, you can see that the first operator is all dagger operators. So we construct actually a state that we call the loop string hadron basis state. That is, you take this plus plus, that is all dagger type operators, take some integer power of this operator and act on strong coupling vacuum, you get a local description of a gauge invariant state that we call the loop string hadron state. This L is the loop quantum number, this IO is the incoming and outgoing string quantum number. And I mentioned it mathematically, the hadron is equivalent to presence of both incoming and outgoing string. So that is why these quantum numbers are sufficient to characterize the gauge invariant Hilbert space at each lattice site for a 1D lattice. Now see, this is some operator that has purely bosonic content. This is loop. That is why this number, this integer, that number can take any integer value starting from 0 to infinity, whereas these are fermionic operators, so they have a fermionic content, a single fermionic content. So they can actually take values only between 0 and 1. And I mentioned that when you construct these local states are defined in each lattice sites. And you have a connection between them, that is the extra abelian Gauss law that is part of this formalism. And in terms of these quantum numbers, this abelian Gauss law constraint is something like this relation. This is an algebraic relation. But these, in the eigenbasis of this is an algebraic relation, and you will get the constraint that has to be satisfied. Okay, physically, to understand this construction intuitively, you may look at this picture where, for example, if you look at this site, these blue dots are particular lattice sites, and these are all the global states. I mean, the original string states or the original gauge invariant states that were constructed on the original lattice. How do we map that to our local description of loop string hadrons? For example, this is a string state that contains a quark anti-quark pair, and here, if you look at, say, for this site here, you see 1 unit of flux is flowing. So that is why this NL quantum number is 1. There is only one outgoing string present in this site. So this NO is 1 and NI is 0. So this is one particular LSH loop string hadron state at one site. Similarly, you can describe each of the states by these 3 quantum numbers. What becomes important is that you need to have this continuity of flux. This continuity of flux is the abelian Gauss law. So this abelian Gauss law states that along any this dotted vertical lines, these gray lines must be continuous. If that is that, then you are getting a global gauge invariant state as well. Okay, so this is some illustration just. And you can now write the operators that describes the dynamics in terms of your loop string hadron quantum numbers. And finally, you can write the Hamiltonian. This is the Hamiltonian written completely in terms of loop string hadron formalism. Now, if you just randomly look at this Hamiltonian, this looks very different from what the Hamiltonian of the Kogut-Susskind Hamiltonian is for this case. But at the end of the day, you actually produce the identical spectrum. This Hamiltonian has the same spectrum, same Hilbert space as the Kogut-Susskind Hamiltonian. But the benefit is that you are completely doing everything in terms of only gauge invariant variables. Your degrees of freedom for this Hamiltonian is gauge invariant. The Hilbert space is gauge invariant. Okay, so as I mentioned that we see some practical benefits using this loop string hadron formalism. What are these? First of all, you don't need to impose the Gauss law constraint that you had to do if you're using the original Kogut-Susskind Hamiltonian. And if you do that, since this is a SU2 gauge theory, you can write the gauge theory Hilbert space in terms of angular momentum states, angular momentum Hilbert space, and then imposing Gauss's law. What you get when you get a physical state, that is actually a linear combination of many different states. So Hamilton, and this number of terms in any such linear combination grows exponentially with the system size. So any Hamiltonian simulation with this type of linear combination states is very expensive. Whereas the loop string hadron state that I described is actually one sparse. Like your one physical state means one set of one quantum number. There is no linear combination involved. And your Hamiltonian involves ladder operators in terms of this loop string hadron quantum number. So clearly the Hamiltonian acts on one state, gives you another state, doesn't give you some linear combination. So this is particularly important. That is why when we calculate the computation complexity or compare the complexity for the all possible formalisms available, we see that this loop string hadron is actually working much better. Here, this is the overall computational complexity of time complexity for the loop string hadron formalism, and that is almost equivalent to that of the purely fermionic formalism. Now, the purely fermionic formalism is very specific. It is only available there. It is only there for 1+1 dimension, that too with one boundary condition, that is the open boundary condition or fixed boundary condition. It is not there even for 1D periodic boundary condition. But the loop string hadron is more general. It can be generalized to any dimension, to any boundary conditions and all. Yet the cost is almost comparable. So that makes this loop string hadron formalism quite a good candidate for the future Hamiltonian simulation studies. Now, since I don't have much time, I'll not go into detail. There are some complications when you do this loop formulation in higher dimension, but this loop string hadron formalism comes with a particular trick, basically this point splitting trick, where this one particular lattice site is splitted into two lattice sites, and this local loop loops that were available within the prepotential framework now splits into a set of two loops at these two virtual lattice sites.
What's the problem you are solving now?
Okay, I'm going to the higher dimension. Let's say you have the placket term in your Hamiltonian.
Right. You are finding way out from what?
Way out. Okay, the way out thing should go later. Okay, so let me state the problem. The problem is that when you do this formulate the prepotential formalism or the loop formalism for SU2 gauge theory in 2+1 dimensions, you can get, like when I described the 1D case, I saw there is only one loop quantum number. But when you go to higher dimension, there are many loop quantum numbers. I mean, you can imagine that one particular site loop can flow from one direction to another direction, and there are more than one possibilities in 2 dimensions or 3 dimensions. So all these loop states, they actually form an overcomplete basis. There are certain constraints, those known as Mandelstam constraint, that needs to be imposed to get the orthonormal loop basis. Now, this Mandelstam constraint is a nonlinear constraint. It is very difficult to analyze for higher dimensions, so 3 dimensions and for SU3. So that is why we have found a prescription to bypass this Mandelstam constraint, that we perform a virtual point splitting when your one particular lattice site is actually splitted into 2 lattice sites, such that those 6 possible loops that were present within the prepotential framework in 2 dimensions for the original case is now translated into the loops at one of these 2 virtual sites. Now see, these are the sites of a triangular lattice or hexagonal lattice. So their loops can only flow from three directions. So the counting of constraints and all actually take care of this Mandelstam constraint. So this Mandelstam constraint actually translated to another abelian Gauss-Law constraint. Like here you have one extra link direction. So you had the abelian Gauss-Law constraint for original lattice, for this link, for this link. Now you have another abelian constraint for this link. That actually compensates the Mandelstam constraint. So now in this formalism, all your constraints are exactly equivalent.
This is in which dimension? This is in which dimension?
This is the demonstration in 2 dimensions. This can be done in any dimension. There is proof.
And the spectrum is same with these.
Spectrum is same. Exactly. Spectrum is same, without losing any generality. Okay, so for example, then the loop string hadron formalism in 2+1 dimension becomes particularly good because this is you are adding matter field to the theory in the local formalism on the square lattice, like the original thing. Now with this point splitting scheme, what we do is we put this fermion at this one additional lattice site. Now, remember, we are doing this LSH formalism where everything is local description. Now, locally, if you look at this is a 3-point vertex. If you look at this is a 3-point vertex. You know the loop structure, everything, that is very simple. And if you look at the matter, how matter couples with gauge field, this particular one is like just a 1D lattice. So whatever I have described so far for 1 dimensions, it's actually generalized directly to 2 plus 1 dimensions. And this 2 plus 1 dimension, the placket looks something like this. So the placket has many more vertices, not just 4 vertices, but each of the vertices, the local structure is very simple and they're all same. And you have the constraint that is sitting everywhere on each link. I'll describe it a bit. If you go to higher dimension, as Nilmani was asking, this point splitting works like this, that one particular site in 3 dimension is actually splitted to this 4 sites plus 1 matter site. So still the local structure remains exactly same everywhere. Your placket looks complicated, but the locally everything remains same. So this is the main feature of this LSH formalism, that whatever higher dimension you go, your coupling to gauge field, the self-coupling of gauge field is always as complicated as that was in 2 plus 1 dimension. That is the minimal case. And matter gauge field coupling is always as simple as that was in 1 plus 1 dimension. That is the minimal case. So this is expected to be useful, because whenever, whichever higher dimension you go, whatever development, whatever hardware algorithm you prepare for lower dimensions is actually can be used straightforward. Just higher dimensions means you need more and more resources. That's all. But the complexity part is taken care by the construction itself. Okay, now I'll just briefly mention an application in context of digital quantum computation. Here in this work, we have found the digitization of this LSH framework. We have solved Gauss's law on the digital quantum computer. So let me just briefly summarize what I discussed so far. The LSH formalism has 2 key ingredients. First, it has a local SU2 invariant Hilbert space. For a matter gauge vertex, this Hilbert space is characterized by these 3 quantum numbers. For pure gauge vertex, these are 3-point vertex. You have 3 loop degrees of freedom. So given here, these only appear for d greater than 1. And also you have a, okay, yes, this loop quantum numbers can take values from 0 to infinity. And you impose a cutoff, and you can restrict that to be a maximum cutoff, Jmax. Now, there exists abelian Gauss law constraints for each link present on the lattice. In d plus 1 dimension, this link is always a link that connects a quark and a quark site. The abelian constraint takes, abelian constraint takes this simpler form. For higher dimensions, like d equal to 2 onwards, a link can be a link that connects a matter site and a gluonic site. This is the form of abelian constraint that you have in this case. And for the gluon-gluon side, this is the kind of abelian constraint that you have, where you don't have a link, there is no matter. So these are the all forms of abelian constraint. These algebraically look different, but okay, now how do we digitize?
So what happened in the, sorry, you are doing this splitting only for the gauge part, is it? The matter still sits somewhere in between in the...
Matter, yes, like this is the scheme. Like the matter field was originally on the same lattice side. Now matter sits
there
here.
And okay.
Here in this site, you have matter and the gauge field, as I described for the 1-dimensional case. You have an incoming gauge field, outgoing gauge field, and
That's
matter.
right.
So here you can construct incoming strings, outgoing strings, and flow of flux.
Right.
All. And these are the orientations of loops. Like on the original site, you can imagine that this is a site, you can have a Wilson loop state or a string state. A Wilson loop state can pass through it. So this LSH formalism is kind of, you have a Wilson loop state or a string state on your lattice, and you take local snapshots at each lattice site. Whatever the local snapshot is the LSH. It is exactly same.
Yeah.
Okay, so I will not go at all into detail of this digital computation, but I just mentioned that this loop quantum number, this NL can be any integer, and this higher dimensional loop quantum numbers else, those can be higher. integers as well, and one can expand this in binary expansion and can directly map it to qubit state. So this is the qubitization of this loop string hadron quantum numbers. This string quantum numbers are already can take values 0 and 1. So these are already in the qubit language. The loop quantum numbers can also be mapped in this language. And so this is a very straightforward gauge invariant qubitization of the gauge theory. And here I'll not go at all detail. I don't think this is very clear to you as well. So, but these are some quantum circuits or oracles that actually checks for the Abelian-Gauss's law, that whether that is being violated or not at on each of the particular link. Now see, this is the circuit construction for the one-dimensional link, and these are the circuit constructions for the higher dimensions. But you'll see that roughly, if you vaguely look at this circuit looks almost the same. So even if the point is that even if you go higher dimension, the hardware or the oracle that you are constructing for lower dimension remain useful. That is the most important feature or usefulness of this LSH for formalism, or using it in context of quantum computation. Okay, we can also try to find the qubit cost, how many qubits do you need to describe this LSH state for at one particular lattice site. This is something important in the present thing. I'm not going into detail. Let me quickly skip and let me show you the graph directly. This is the qubit requirement, the qubit cost per lattice site. There are different variations of Kogut-Susskind formalism, where here is the description where you see the purely local structure within the Kogut-Susskind formalism. This is the standard rigid rotor formalism of Kogut-Susskind, and this is the loop string hadron formalism. But in loop string hadron formalism, you have the Abelian-Gauss law constraint that you can actually solve. And if you solve this Abelian constraint partially, you get some lower cost. And if you solve the Abelian constraints completely, you get a much lower qubit cost in terms of this. So it depends on the problem that which of this formalism we can take. This is some kind of optimization that has to be done for practical purpose.
Sorry, what's the x-axis again?
Sorry?
What's the x-axis?
Oh, the x-axis is the maximum cutoff that you apply on your lattice, like for a given cutoff. Actually, you have infinite dimensional Hilbert space, but then you put a cutoff in your theory, that gives you a finite dimensional Hilbert space. So this is the log of this cutoff. Okay, I think, can I take 5 or 10 minutes to go through this analog quantum computing part, or should I skip this? Okay, since there is no reply, let me continue.
Rishi?
Yeah, we can have 10 more minutes. That's fine.
Okay. Okay, so now I'll describe in summary of how this formalism can be actually useful in context of analog quantum simulation as well. Okay, we have discussed this in the beginning of my talk. What does it mean by analog quantum simulation? So that this is written just here. The concept of analog simulation involves mimicking a quantum system described by a Hamiltonian, or that is called the simulated Hamiltonian, by another completely different quantum system that we call a simulating Hamiltonian. So you have two parts, one simulated system of interest and one simulating Hamiltonian, that is your toolbox. The idea is that if it is hard to compute the simulated Hamiltonian with any other available method, then it can be mapped to a second Hamiltonian, and that Hamiltonian can be studied in an experiment by suitable tuning the parameters. Basically, system of ultra-cold atoms or ions trapped in optical lattices, those serve as an excellent quantum simulators. And there has been much progress over the last decade towards constructing these quantum simulators for various physical problems, both from condensed matter physics and all. So there are other platforms as well, and they are being explored day by day now, but these are kind of most popular or old two platforms, much used platforms as well. Okay, so here is a work that recently we have proposed a cold atom quantum simulator for the string and hadron dynamics in non-abelian gauge theory. This is a study in 1+1 dimension LSH formalism that I described so far. So it describes the dynamics of string and hadron, is quantum simulated by a cold atom systems. And the important is that this is within the reach of the scope of present experiment. This is not some science fiction. Okay, so as I mentioned, we need a simulated system and a simulating system. The simulated system that we are taking is the SU2 gauge theory in 1+1 dimension described by Kogut, Susskind, Hamiltonian. And the simulating system that we are choosing is a system of ultra-cold fermions trapped in optical lattices that is described by the Hamiltonian of some ionic Hubbard model, some condensed matter model. More importantly, at the simulated Hamiltonian, we have already established this LSH Hamiltonian is exactly equivalent to Kogut, Susskind Hamiltonian. So we are basically starting with LSH Hamiltonian because in that case, we are actually getting a manifestly gauge invariant simulation scheme. And we also find this simulation to work at a long range of couplings in the original, in the gauge theory. Okay. I'll not go into very much detail, but the simulated Hamiltonian, we start with some approximation. What is the approximation? We have described that there is some NL quantum number and some NI-NO quantum numbers. Now, this loop quantum numbers for a lattice with a particular boundary condition and some fermionic content, and after solving Gauss's law, this NL quantum number is actually a non-dynamic quantum number for 1D case. That is the reason why 1D gauge theory really has no dynamics. It's basically dynamics of fermions, so dynamics of strings that we'll see. So at this point, we make a main field ansatz. Just let's say with all the states, this NL, the expectation value of this NL is very large. So we take this to be kind of a sea of strings, a sea of loops, and you have the strings in the presence of this sea of loops. This is the approximation that I am starting with, the very first approximation. And this is a valid approximation in the weak coupling regime, because in the weak coupling regime, when G is very small, G goes to 0, then if the very large values of NL actually do contribute to the finite spectrum of the theory, finite energy or the low energy. So this is a good approximation, valid approximation for the weak coupling regime, but we'll see if we can go beyond weak coupling regime as well. Okay, so we have the loop string hadron Hamiltonian given here. Now, if you look into detail at the form of loop string hadron Hamiltonian, this electric part of the loop string hadron Hamiltonian, depending on the Ni and No or the matter content of this site, this takes these forms. Now you'll see that for these three cases, they are exactly same. Only for one particular matter configuration, this electric Hamiltonian takes a different form. So we call this to be a approximated electric Hamiltonian plus some correction. The correction is appearing in the statistical limit. This correction is appearing only in 1/4 of the cases when this configuration is there, fermionic configuration is there. And of course, the matter Hamiltonian doesn't involve NL. So matter Hamiltonian is exactly exact, the mass Hamiltonian. And we have the interaction Hamiltonian. This LSH interaction Hamiltonian looks really complicated. But since we have made the ansatz that NL is actually very large and average quantum number, within this ansatz, if you take NL plus 1 equivalent to NL, this interaction Hamiltonian becomes very simple. This is just a simple form. So now let us compare what do we have. We want to simulate the system. This is the weak coupling regime of lattice gauge theory. This is the strong coupling regime of lattice gauge theory. The continuum limit lies here. It's expected to be lying here. And this is the where the lattice gauge theory works perfectly. Now we have some approximated Hamiltonian within the mean field ansatz written here. So here, the weak coupling limit, this electric field is not very important because G is small. and we give this, take the approximated version of this loop string hadron quantum number. Mass term is exact for both the cases. And okay, here when we are looking into the strong coupling limit, of course, in the strong coupling limit, this electric field term becomes important because G is very large. So there we are adding the correction term to the Hamiltonian that I mentioned, that 1/4 of time there is some correction that appears in the mean field Hamiltonian. And the approximate Hamiltonian, we are taking the same for both the weak coupling and the strong coupling limit. In the weak coupling limit, it is good approximation, and this term contributes most to the spectrum. In the strong coupling limit, this approximation is very bad, but again, in the strong coupling limit, the Hamiltonian is mostly diagonal, so this term doesn't matter much. So from this, we are mapping it to a system of Hubbard model. This is a set of fermionic atoms with two accessible states, plus minus states, that is, those are confined on the optical lattice. And we are doing some kind of exact mapping, like the atomic Hamiltonian or the Hubbard model has all those terms. I am mapping my terms in the simulated Hamiltonian to this set of particular terms in the Hamiltonian. I'm identifying these to be equivalent to my Hamiltonian. And then the interesting part is that as I mentioned, that the strong coupling limit, the electric field Hamiltonian deserves some correction. Like this here, this is only approximated. This is approximated plus some correction. And we are mapping it to the Hubbard model, where Hubbard model, we are having some interaction term as well. And in the limit where this U is large or finite, this interaction matters here. So this is kind of a free theory, free Hubbard model, and this is some interacting Hubbard model that we have in the strong coupling limit. That way we are doing the mapping, starting from the gauge theory Hamiltonian, mapping to this Hubbard model Hamiltonian. So this system can actually has been realized in actual experiment. These are the two experiments that actually done the same dynamics without realizing that it is somewhere related to the is actually simulating gauge theory dynamics, but it's the exactly same framework. And more precisely, we have chosen the parameters or the tuning of parameter that has been used in this actual experiment. Okay, this is just a cartoon diagram of what the dynamics is happening. Let's say this is the strong coupling vacuum of you have your alternate sites are fully filled, you have the lowest energy of the system. So this is the vacuum of the state. Now you can trap two atoms, two different species, this up and down species in one particular alternate wells, and start with this particular state. Now if you allow your atoms to hop and you adjust your laser that you can control this hopping by proper value of the parameter that is exactly equivalent to that parameter in the gauge theory, you will end up with this state. You have one atom here, one atom here. Now this is equivalent to the hopping here in the gauge theory Hamiltonian, where out of vacuum you produce a string state. Now again, if you hop one of the atom here, what you get is another string state, string hadron state. So this is how this dynamics of atoms is mapped to the dynamics of string dynamics. So basically you may think that these are just fermions, so these are just quark, but this is the feature of loop string, your fermionic quantum number that is giving you a string end or something that is basically contains one fermion and a boson. So this is basically string operator. These are string hopping. So that way you can get rid of the background bosons as well. Only the relevant boson that is required to have your gauge invariant dynamics for a one-dimensional lattice can be captured by this fermionic Hubbard model. And here you can see this is the numerical benchmarking of the scheme that I propose, that this is the spectrum of the full gauge theory. This is the green one is the approximate, and this is approximated LSA, the approximation that I made. And this red one, maroon one is the Hubbard model system. Now you will see that as you differ from the weak coupling limit, this is the very weak coupling limit and this is the very strong coupling limit. If you differ from the weak coupling limit, you see your approximation is actually bad. Your approximation is going bad. But the ionic Hubbard model Hamiltonian is actually mimicking dynamics of the full gauge theory, because we have tuned the parameter and we have tuned the interaction of atoms such that it takes care of the error in the electric field Hamiltonian that was originally there due to making the approximation. So at the end of the day, you produce, and this is the real-time dynamics, looking at the dynamics of the Hubbard model, you see that the dynamics is exactly matching, at least up to this intermediate coupling regime. Now this scheme has some loopholes. First of all, there are some advantages, of course. This is a completely SU2 invariant observable. You don't have to think of imposing Gauss's law, because that for a condensed matter system or a quantum simulation is a real difficult job, and different groups are really struggling to work with that part of the problem, how to take care of Gauss's law, because Gauss's law or gauge theory, the condensed matter systems are not gauge theory. So simulating a gauge theory is really difficult. However, in this formalism, you can really forget about that part. And this is a very good approximation for the weak coupling limit. This works well in the up to intermediate coupling regime. It doesn't work very well to the due to this condensed matter system faces some phase transition that is not there in the original theory. That is why you cannot access the very strong coupling regime with this scheme. That has to be modified or find some other scheme if you want to simulate the strong coupling limit. But again, strong coupling limit is something that you can work with the classical computer. But for large lattice and for weak coupling limit, that is almost impossible to work on the classical computer. So that is where this becomes important. Okay, so let me summarize. I'm already out of time. So we are trying to find a suitable formalism, that is the loop string hadron formalism, that will work better than the original Kogut-Susskind formalism for the purpose of quantum computation, because it takes care of the complication. It gives it kind of maps the SU2 gauge theory to kind of a Schwinger model, because only the non-triviality that remains is a abelian constraint on one link. Other than that, it is completely solvable. Or not solvable, it's much more simpler to deal with. And so the direct generalization of that to SU3 in 3+1 dimension offers really good hope for quantum computing actual QCD. And we have seen that the immediate and straightforward applications in both analog and digital simulation has been found to be really useful. Okay, so there are some ongoing projects that I'm working on. Of course, there are some theoretical projects that deals with SU2 gauge theory with a finite cutoff and understanding the effect of cutoff. I'm also trying to use the classical computer at its fullest by doing some tensor network calculations that can be done on a classical computer, but yet offers some insight towards quantum computing. And also some generalization of analog quantum simulation scheme that I presented here is in progress. And of course, develop the framework for full QCD. These are my collaborators towards this project. These are basically AMO people who are working with whom we are working the analog quantum simulation part, and including this one. And they are all my collaborators here. Thank you very much.
Thanks, Indrakshi. So I guess we already had a lot of questions.
May I ask one more?
Yeah, sure.
Yes.
Go ahead.
I got a little confused in that last part. So the mapping was done in mean field. Is that right? The
Yes.
mapping to Hubbard model? And
Yes.
how did you get the real-time dynamics of SU2 gauge theory? That was done in mean field? You compared the...
It's mean field. It's mean field
So
for the
fast. This is mean field in what? Sorry, that was my first question.
Mean field in bosonic part of the theory. The theory has a loop string hadron. The string and hadron are fermionic content of the theory. And loop part is the bosonic. Now, when you are looking at a one-dimensional theory, you don't really have dynamics for gauge theory. because that is why you don't have any dynamics for a 1D theory without matter. It's all fixed. So that is why whatever dynamics you have is actually dynamics of matter or dynamics of strings. The phenomenon that you can see in the real-time dynamics is the string elongation of string, string breaking, pair production. Those are the dynamical phenomena that you can observe.
Okay.
So those are the things that I am observing in the simulated dynamics.
Okay. And the full SU2 results were obtained how? You compared the analog results with the, go to, yeah, these, yeah.
These are exact diagonalization.
Exact diagonalization, okay. Okay, fine.
Okay, so thanks, Indra.